Okay, I will start class in 2 minutes. I'm waiting for the students to join. There are 32 participants. I will wait for 1 more minute. Okay, there are 35 students have joined. Let me start the class. Today I'm going to start lasers. Okay, this part of module 3 is there in your second internals. Okay, I have already shared the notes, and let me start the class. Okay. Okay. Uh, Before starting, okay, wait. Okay. Before going into the details of laser, let me tell you what is the meaning of laser. Laser is the abbreviation of light amplification by stimulated emission of radiation. You just don't take it as a abbreviation, but just try to understand it. There is a term known as light amplification and also stimulated emission. These two things are very important in getting laser radiation. Okay, I will explain what is the meaning of these light amplification and stimulated emission in this class. Okay, uh, before starting uh, before starting the syllabus part of laser, one should understand uh, the basics of laser source. Okay, and what is the difference between the normal light and laser light. Okay, the first thing is monochromaticity in laser is a unique characteristic. Okay, laser light is monochromatic, whereas normal light is non-monochromatic. Monochromaticity means we have only one frequency or one wavelength for laser, whereas normal light will be emitted in various wavelengths. Okay, and the second concept of the second difference between laser light and normal light is the coherence. Coherence means the phase difference between various rays emitted by the laser source is same. That is, the crest of one laser ray will match with the crest of the other. Okay, I hope you understand. Laser radiation contains many rays, and all the rays will have same phase difference. Okay, whereas in normal radiation, the phase difference is not there. Okay, sometimes the crest of one radiation may fall on top of other, and we may not get the bright light. Okay, that you might have seen in your domestic incandescent lights. You can see some zero intensity spots in the light. That is because of non-coherence of normal light, whereas laser is highly coherent. Okay, and laser is collimated. That means it has unidirection. Okay, laser will move in a single path, whereas non laser sources such as incandescent bulb will emit radiation in all possible directions. And the last one is the power density of laser. Power density means energy emitted by the laser is of the order of 10 power 9 watt per meter square, whereas it is very less in normal light. If you expose your skin for a long time, then laser will definitely going to burn the skin. That is nothing but power density of laser is very high. Okay. Now, these are not very much important from the point of view of examination. This is only for the understanding sake. Let me start the main proceedings of the class. Okay. Wait, I just want to remove this. Okay. Where shall I take it? Okay. Look at here. The first concept or the first question in laser part will be like this. You have to explain three phenomena. One is induced absorption, second one is stimulated emission, and third one is spontaneous emission. Okay. The question will be for 5 to 6 marks in the examination. They will ask you to explain the concept of induced absorption, stimulated and spontaneous emission. Okay. Let me explain one by one. The induced absorption is the phenomena in which we incident a photon on the ground state atom, and the atom will absorb this incident photon and it will go to the excited state. I hope you all know that the radiation will be absorbed by electrons, right? In the atom, if we incident radiation on the atom, electrons will absorb the radiation and they will go to the excited state. And that means what? Electrons are the part of atom. If electron absorbs radiation means atom absorbs radiation. Okay. If electron goes to the excited state means atom itself goes to the excited state. In explaining laser, here these energy levels are applicable for the atom. They are not the energy levels of the electron. Okay. You have to make sure that electron absorbs energy and hence it is equivalent to atom or molecule absorbing energy. Okay. Therefore, I am talking that in the laser, the atoms which are in the ground state will absorb the radiation and atom goes to the excited state. Okay. Just observe the word atom. I'm saying atom absorbs radiation and atom goes to the excited state. Don't get confused with any other thing. Okay. I'm not talking about the individual electron. Here entire atom or the molecule itself absorbs the radiation. Okay. I will show it with a animation. You see, if I incident a photon, this is the photon. If it hits the atom in the ground state, then atom will absorb the radiation and goes to the excited state. This is known as induced absorption. The word induced means we are actually supplying something for excitation. The atom itself will not go to the excited state. We are making that atom to go to the excited state. That is the meaning of induced absorption. Okay. And then you know that, I have written a expression for this also. Atom, when it absorbs photon, it becomes atom star. Atom star means excited atom. Okay. Now I will explain spontaneous emission. Spontaneous emission means the atom which is now excited to the excited level will not stay there for a long time. You know that in nature, every particle has the tendency to occupy the lowest possible energy state. Therefore, atom in the excited state comes back to the ground state and it emits the photon which it has earlierly absorbed. Okay. Let me repeat once again. Atom in the excited state comes back to the ground state by emitting a photon. And this happens on its own. We need not to do anything. It happens on its own. It is similar to the concept of water flowing from higher altitude to lower altitude. That's it. Okay. The excited atom de-excites by emitting a photon. I have an animation here. Here the word spontaneous means on its own, natural. Okay. We need not to do any work. You can understand this by this animation. You see, the atoms comes back to the ground state. Again, I will show. Atom comes back to the ground state by emitting a photon. You see, there is a photon emitted, and there is no addition of photon has been taken place. Atom has been excited by absorbing a photon, and atom is de-excited by emitting a photon. Photon number is not increased. Okay, this will not give rise to any light amplification. Light amplification means the number of photons should add up. If I send one incident photon, the photon should be absorbed by the atom and at least two photons should be emitted. Okay, at least two photons are required. But in spontaneous emission, we are just getting the absorbed photon as, we are getting only one photon, which is nothing but the absorbed photon earlier. Okay. Pratham K. Gujjar, what is your problem? Why you are raising your hand? And your video is also on. And this video is actually recorded. Why you are doing that? Don't you understand? Pratham K. Gujjar, your video is on. Okay, switch it off and down your hand. Okay, now therefore spontaneous emission will not help us in getting laser. Okay, therefore we have to go for one more concept that is known as stimulated emission. Okay, I will explain it in a while. Just understand this spontaneous emission by this equation. Atom in the excited state, atom star, now comes to the ground state and emit a photon. This summarizes the spontaneous emission. Let us go to the stimulated emission. Here, in the stimulated emission, the excited atom actually will not come to the ground state on its own. Okay, this excited energy state is more stable than the one which we have discussed in the spontaneous emission. Okay, these type of states are known as metastable states. I hope you understand what is the meaning of stability of a energy state. Let me tell you, the ground state is the most stable state. Every atom will be in the ground state for a long time. Therefore, lifetime of the ground state is very high, whereas lifetime of excited state is very low. It is of the order of 10 power minus 9 seconds. That is 10 nanosecond. 1 nanosecond is the lifetime of excited state. That means if you excite an atom from the ground state, within a nanosecond, that atom will come back to the ground state. Okay. But there are few energy levels. Certain materials will possess that type of energy level in which the excited state is more stable than the normal excited state. Okay. The atom will stay there for millisecond. Okay. These type of states are known as metastable state. Let me explain once again. Ground state are highly stable states. Atoms will stay there for a very long time. But excited states are having very short lifetime. The normal excited states will have the lifetime of the order of 1 nanosecond. That is 10 power minus 9 second. But there are some special excited states available in certain materials which will have the lifetime of millisecond or 10 power minus 3 second. You can again argue with me that what is the use of it? One is nanosecond, another one is millisecond. We cannot actually distinguish between nano and milli in our lifetime, right? But you just compare 10 power minus 9 with 10 power minus 3. There is a 10 power 6 second difference between millisecond and a nanosecond. It is almost 10 lakh times stable than the ordinary excited state. Let me tell once again, in some materials, there are two types of excited states available. One excited state having very short lifetime of nanosecond and some other excited states of millisecond lifetime. Okay, these millisecond lifetime excited states are known as metastable states, and you already understand that metastable states are 10 lakh times more stabler than the ordinary excited state. Okay, and therefore, okay, is there any issue with slideshow? Slide shows are changing or not? If not changing, please raise your hand. I am in the stimulated emission. Okay, 3 participants have raised the hands. Okay, let me go back to the slide once again. Wait. I will go back to the slides once again. Stop share, screen sharing. Okay. Okay. Can you see the slide? If you are able to see, now raise your hand. Okay, 2 participants raised hand. I think you are seeing stimulated emission, right? Okay. Now, let me go back once again. Okay. I have actually distinguished between normal light and laser light. Laser light is monochromatic, coherent, collimated, and having higher power density. Okay, this is what I have explained. Okay. Please, someone unmute yourself and tell me whether you can see this slide comparison between normal light and laser light. Or please write in the chat box. Can you see this slide? Comparison between normal light and laser light. Okay, charts are coming. Let me read. No, sir, we can only see the first page. It's showing the first slide again. Is it so? Okay. Okay, still on the first slide. No, sir. Okay, let me try once again. I'm sure I'm stopping sharing. Now, can you see? Sir, permission to unmute is not given. Okay. Just write in the chat box. Yes. Yes. Okay. I got it. Now you can see the comparison between normal light and laser light. Is it so? Okay. Charts are coming. Yes. Okay. Thank you. Thank you. Leave it. Just let me move on. Okay. Now in this slide, I have made comparison between normal light and laser light. Okay. Monochromaticity is the first difference between laser and normal light. We are getting only one wavelength. Coherence, that is phase of various rays in a laser light matches with each other. That is known as coherence. And collimated means, collimated means unidirectional. Laser light is a unidirectional light. Okay. And then power density is of the order of 10 power 9 watt per meter square, very highly energetic. Okay. After that, I have explained the concept of induced absorption. There are 3 main mechanisms which we have to learn in laser action. First one is the induced absorption. Please write in the chat box. Can you see this slide? Induced absorption. Yes. Okay. Thank you. Okay. Thank you. I got it. Okay. Now, in the induced absorption, what I have explained is the atom in the ground state will absorb a radiation. This is the radiation, and atom will go to the excited state. Okay. This is known as induced absorption. Atom absorbs photon and gives excited atom. Okay. Now, the second concept is spontaneous emission. The atom on its own comes back to the ground state by emitting the photon which it has already absorbed. I have given one photon, I got one photon. Okay, this will not called as amplification. Okay, I should get at least 2 photons to call it as amplification. Okay, and this spontaneous emission takes place in actually from a normal excited state to ground state. Normal excited state means the energy states with nanosecond lifetime. Okay, the atom will not stay for very long time in the excited state. On its own, it comes back to the ground state. Okay, that is summarized by the equation: excited atom is equal to ground atom plus photon. Here there is no concept of amplification. To get amplification or to get additional photon, what I have to do is I have to introduce the concept of metastable state. Metastable states are the special type of excited states which will be more stable than normal excited states. Okay. In these states, the atom will tend to stay for a long time, and this atom can be brought down to the ground state by incidenting a photon. That is, atom on its own not coming to the ground state. I am actually somehow disturbing the atom in the excited state and making that atom come to the ground state. Okay, in the animation you can see here. In the animation you can see here. If I supply a incident photon, this excited atom will absorb that photon and comes back to the ground state. And while coming back, it will emit not only one photon, but two photons. One is the incident photon and other one is the photon due to this de-excitation. Thus, a single photon is now converted into two photons. Both photons now travel in the same direction with the same wavelength and same phase. Okay, thus we are going to get laser radiation. Therefore, the requirement of metastable state is there in getting laser action. Okay, therefore, these are the three fundamental processes involved in the laser. Okay, in the examination, they will directly ask you to explain induced absorption, spontaneous emission, and stimulated emission. Okay, now I can summarize this stimulated emission by this equation. This excited atom, when absorbs a photon, it comes to the ground state and emits two photons. Okay, this is what stimulated emission is. Okay, now I will move to the important question from the point of view of examination. Okay, in the examination, they will ask you to obtain the expression for energy density of incident radiation. I have said that light will be absorbed, right? I require photons to excite the atom, and also I require photons to make them come back to the ground state, right? Therefore, I require some energy to excite the atom and to de-excite the atom in lasers, right? That energy density expression you have to derive in the examination. Okay, and also sometimes they will ask you to obtain expression for energy density in terms of Einstein's coefficient. Okay, this is very important. Einstein's coefficient. In a while you will understand what is the meaning of this Einstein coefficient. Okay, let me start the derivation. I will consider a two-level system, okay, on which I am incidenting a radiation, incident radiation of energy density. Energy density means energy per unit area. Okay, suppose there is a semiconducting material from which I am going to take lasers. I have to excite the semiconducting material using the incident radiation. Okay, the incident radiation per unit area is known as energy density. Okay, energy of the incident radiation per unit area is known as energy density. Okay, this is UV, U nu. I will call it as U nu. Nu is the frequency. Okay, frequency of the incident photon. Again, I will repeat. I am considering a two-level system. Okay, I am considering some carbon dioxide molecule. Okay, which have two energy levels. One is ground level, another one is excited level. For example, okay, I am considering a two-level system on which I am incidenting a radiation of energy density U nu. Okay. Now, this, what are the processes that is going to happen inside the material? The carbon dioxide, for example, carbon dioxide molecule will absorb this incident radiation and it will go to the excited state. Exactly, it is the case of induced absorption. Okay, induced absorption will take place as soon as I incident some energy on the carbon dioxide molecule. Then that molecule will absorb the energy and goes to the excited state, right? Now, the rate of this induced absorption, that is energy absorbed per unit time, depends on number of atoms present in the ground state, right? Number of atoms or molecules present in the ground state. That is because if there are no atoms in the ground state, then there is no absorption, right? Therefore, this rate of absorption is directly proportional to number of atoms in the ground state. And also, this rate of absorption is directly proportional to the energy density which is incident. Okay, if there is no energy density, there is no rate of absorption. Therefore, this rate of absorption, this thing you have to understand. Rate of induced absorption is directly proportional to both incident energy density as well as number of atoms in the ground state E1. Okay, let me explain once again. If there are no atoms, there will be no absorption. And also, if there is no energy, there is no absorption. Therefore, both energy density as well as number of atoms are required for absorption. Okay, and the constant of proportionality here is known as Einstein's coefficient. I will call it as B12. Okay, rate of absorption is directly proportional to U nu N1, and constant of proportionality B12 is known as Einstein's coefficient. Okay, I will call this as equation 1. Remember this thing, B12 is the Einstein coefficient which represents induced absorption. Okay, now after absorption, what will happen? Of course, after absorption, emission will happen, right? First is stimulated, a spontaneous emission. The molecule on its own comes back to the ground state. Okay, stimulated emission is going to happen. I don't require any helping atoms or helping energy. The atom in the excited state on its own comes back to the ground state. Therefore, the rate of this spontaneous emission is directly proportional to number of atoms in the excited state N2. Okay, number of atoms present in this excited state E2, that is N2. Isn't it? If there are no atoms present in the excited state, there will be no spontaneous emission, right? Therefore, it is quite obvious. Here again, I have a proportionality. Therefore, the constant of proportionality is required. I will call it as A21. This is the another Einstein's coefficient. Okay, A21 represents spontaneous emission. Okay, A21, that is atom is spontaneously emitted from energy level 2 to energy level 1. Just remember this equation 2. I will summarize once again. I have induced absorption in which I have B12, which is the Einstein coefficient for induced absorption, and I have spontaneous emission. Here, rate of spontaneous emission is directly proportional to N2, and I have defined new Einstein coefficient A21. I have two Einstein coefficient now. Now, there is one more process going to happen inside the material. What is that process? That is the process of stimulated emission. Okay, stimulated emission is the next process. In the stimulated emission, I require a helping aid. I require an incident photon to bring this molecule to the ground state. Okay, I have said that stimulated emission takes place from metastable state to ground state, and these metastable states are highly stable. Therefore, these molecules are they on their own will not come back to the ground state. I require some helping aid, and I incident a photon to bring this atom to the ground state. Okay, and therefore there are two photons released. One is incident photon, another one is stimulated emitted photon. Okay, now this rate of stimulated emission depends on, okay, wait, this rate of stimulated emission depends on both incident energy. You can see there is a photon incidenting on the excited atom. Therefore, this rate of stimulated emission is directly proportional to incident energy as well as number of atoms in the excited state. Again, it is obvious. If there are no atoms, there will be no stimulated emission. And also, if there is no incident photon, there is no emission. Therefore, these two quantities are required to decide the rate of stimulated emission. Again, I have a constant of proportionality. This time, this constant of proportionality is known as B21. Okay, B21. This is the another Einstein coefficient. I have defined three Einstein coefficients now: B12, A21, B21. Okay. Now, you should understand this number of photons absorbed by the system per second should be equal to number of emitted photons per second, isn't it? Number of photons absorbed per second should be equal to number of photons emitted per second. Or in another sense, rate of absorption should be equal to rate of spontaneous emission plus rate of stimulated emission, isn't it? The number of atoms or number of photons which are absorbed should be equal to number of spontaneous emitted photon and number of stimulated emission photon, or the rates of that. Okay. Now, with that understanding, you just see here, this is the rate of absorption, right? B12 U nu N1. Okay, this is from equation 1. This should be equal to rate of spontaneous emission plus rate of stimulated emission, isn't it? Rate of absorption should be equal to rate of stimulated emission plus rate of spontaneous emission. Okay, and I will rearrange this in such a way that I get energy density U nu to the left hand side. Okay, I can rearrange like this. Further, I can take U nu rate of, energy density as common. I can write this, and then I can obtain the expression for energy density as U nu is equal to A21 by N2, okay, divided by B12 N1 minus B21 N2. Okay, these are all algebraic steps. There is nothing much physics has been explained here. Okay, then I will take A21 as common from the numerator and B21 as common from the denominator. Okay, again, this is a algebraic step. Here, B21 is taken common. Also, N2 is also taken common in the denominator. Therefore, I will get this equation 4. You have to try it on your own. Okay, I will not explain that. I will stop here. Okay, in the offline class on Saturday. Okay, I have 6 minutes left. I will finish it up. Okay, I will finish it up. Now, just concentrate this equation 4. I have taken A21 common in the numerator and B21 N2 common in the denominator. Okay. Therefore, I will be left with this type of equation. So try on your own. Okay. Now, I compare this energy density equation with Boltzmann law. Okay, this is a new thing which you don't know. Boltzmann law actually is used to tell the number of atoms present in a given energy level. For example, if N1 is the number of atoms present in the energy level E1, that N1 is related with E1 through this equation. N1 is equal to e power minus E1 by kT. Okay, this is a abstract thing. This was not discussed previously, but here you have to remember this thing. Okay, Boltzmann law gives the number of atoms in a energy level. Okay, this is the expression N1 is equal to e power minus E1 by kT. Similarly, number of atoms in the N2 will be equal to e power minus E2 by kT. If I take the ratio N1 by N2, it will look like this. Okay, this you have to remember. There is no other way out. Okay, and therefore this ratio N1 by N2 can be written as e power E2 minus E1 by kT. Okay, E2 minus E1 means what? What is the meaning of E2 minus E1? This is the energy difference between excited level and the ground level, and that is also equal to the energy of the photon, right? Therefore, I can replace E2 minus E1 as h nu, energy of the photon, according to Bohr's law, right? Therefore, N1 by N2 can be written as e power h nu by kT. Make this substitution in the equation 4. In the equation 4, you will have N1 by N2. Substitute this with e power h nu by kT. Okay. Now, the equation 4 will look like this. U nu is equal to A21 by B21 whole divided by e power h nu by kt into B12 by B21 minus 1. Okay, you have to practice on your own. This is a very important question. This may be there in your second internals. Please practice it today itself. Okay, this is the expression for energy density, but I can simplify this energy density expression further. You have to compare this energy density with the Planck's radiation formula. I hope you remember what is the Planck's radiation formula. In the module 2, you might have seen this equation, right? The energy emitted by the or energy density coming out of a black body is given by Planck's radiation law. Compare this equation 6 with Planck's radiation formula, and you will see that, I mean, forget about this A21 by B21. Just look at this denominator. In the denominator, you have e power h nu by kt into B12 by B21 minus 1. But in the Planck's radiation law, you don't have this term. In the place of B12 by B21, you have only 1, right? That means A21 by B21 is equal to 8 pi by h nu by k, h nu cube by c cube, and B12 by B21 is equal to 1. Okay, that means what? B12 is equal to B21. Therefore, I can decrease the number of Einstein coefficients from 3 to 2. I can actually neglect B12 and B21. I can neglect this suffix. Instead, I can write it as B. Therefore, final expression for energy density of a laser is this one. It is simply A divided by B into e power h nu by kt minus 1. This will give you 7 to 8 marks in the examination. Okay, there will be a question which asks you to derive the expression for energy density of a laser using Einstein's coefficients or in terms of Einstein coefficients. This is the final step. I have already shared the notes. Please go through the derivation, practice it today itself. It is very important from the point of view of examination. It may be there in the second internals. I am not sure, but you have to practice it. Okay, thank you very much for attending the class. I have recorded this class. If you are not able to follow the online class, if you ask me, I will once again do it in the offline mode. Otherwise, you can see it in the YouTube also. Thank you very much for participating in the class. I'm now stopping the class. Okay, thank you.